So we continue. And right now, I want to revisit again the basic system. And I want to relate it to local coordinate system, right? Element local coordinate system. Okay. All right. Right. So what we'll do, okay, is I will write the element, okay, in a local coordinate system. It's ij. Okay. And I will denote my displacements as delta prime 1, delta prime 2, delta prime 3, and delta prime 4. Okay. Now, at the same time, right, I'll look at the same element in the basic coordinate system, right? So what do we need? Right? We need to compute, right, the element relative displacement in the axial direction. Okay. Right. So by looking at this picture, right, I don't care what delta prime 2 or delta prime 4 are, right? Again, assuming that these displacements are not so big, and this is an assumption of the course, right? The only quantities that will contribute to the relative elongation or shortening of the element would be delta 1 and delta 3, okay? And if you recall our previous lecture, right, the element basic displacement, delta prime over bar, okay, was delta prime axial at node J, which is delta prime 3, minus delta prime axial at node I, which is delta prime 1. So this will define for us the basic element displacement. Okay. So as with everything in this class, we can actually go ahead and express it in the matrix form. Okay. All right. So delta 1 comes in with a negative 1, right? Delta 2 is unaffected. Delta 3 comes with a positive 1, all right? And delta 4 is unaffected. Okay. And so that row vector multiplies the column vector of the prime displacements, delta prime 1, delta prime 2, delta prime 3, and delta prime 4. Okay. We can do it this way. And so now, although this guy is a scalar, right, for the case of a truss, I'll still going to give it a number, okay, 1, like this. Okay. So then, delta prime bar, right, as a vector, although this is a one by, just 1 by 1, equals to some matrix, okay. I'm going to call it gamma RBM, okay. Times delta prime. Okay, so this guy is 1 by 1. This guy is 4 by 1. This guy is 1 by 4. Okay, so RBM, recall, stands for rigid body mode. Okay, and so what this operation does, right, what this matrix does, is it takes a generic displacement state in a local coordinate system. Okay, I'm going to give you 4 numbers, right, that give you the displacement state of the structural member, and extracts from it the quantity that you need, which is a basic displacement. Okay? So you feed on the generic displacement state, you get a basic displacement state. Okay? And the operator that makes that happen is this gamma RBM matrix. So gamma RBM basically extracts, or not extracts, but I would say removes rigid body modes from delta prime, right? From a general vector of displacements. Okay, removes rigid body modes, right? And boils the displacement vector down to basic element displacement. Okay, because we know that's the only displacement, right, that will contribute to the forces in the system. Okay. This guy is denoted by delta overbar prime underbar. Okay. Okay. All right. So that's an important relationship to keep in mind. Okay, let me write this down again. Delta prime overbar underbar. Okay. Basic element displacement equals to gamma RBM times delta prime. Good. This is rigid body mode matrix. Okay. And this is element displacement in the local coordinate system. Okay. Right. All right. So what would the relationship then, okay, would look like between the forces? So let me pose that question. Relationship between the basic force and the local force vector. Okay. Well, let's try to do this through the work arguments, just like we did for the global and local. Okay. Right. Right. So let's look at the local. W equals 2. Right? Remember, force times the distance. Okay. What's our force vector? F prime 1, F prime 2, F prime 3, and F prime 4. Okay. What's our displacement? It's a vector delta prime 1, delta prime 2, delta prime 3, and delta prime 4. Okay. We have that. In the basic system, work equals to, right, F over bar prime 1, which is a basic force, right, times delta over prime 1, basic displacement. Okay. Next, I will use the relationship, okay, between delta prime and delta prime over bar. Prime 1, right, times minus 1, right, gamma RBM minus 1, 0, 1, 0, times delta prime 1, delta prime 2, delta prime 3, delta prime 4. Okay. And so now, if I am to equate these two, okay, you can see right? That we have a vector of delta primes here, we have a vector of delta primes there. So the two quantities are equal, right? Then this quantity must equal to this quantity, right? Or f prime 1 equals to what? Actually, let me state it as a vector, right? So just take this vector here, okay, and compare to this vector there, and you find that f prime 1, f prime 2, f prime 3, and f prime 4, okay, equal to minus 1, 0, 1, 0 times f prime over bar 1. Okay. And so this guy here is precisely gamma RBM, but transpose. Okay. So again, you see this pattern of a transpose relationship, right, for the forces. Okay. Right, and that comes from the relationship between the kinematics and the equality of the work. In other words, f prime equals to gamma RBM transpose times f over bar prime. So the basic force is related to the force in the element local coordinate system through the transformation given by gamma RBM transpose. Okay. This is a transpose of the rigid body matrix gamma RBM. Okay. So again, a very important relationship that will come in handy. All right, so then let's start putting things together. Okay, so what do we know? F prime, right, over bar, under bar equals to the basic stiffness, EA over L, okay, times delta prime over bar under bar. Good. Okay. Now, we also know, right, that equals to EA over L, right, times minus 1, 0, 1, 0, right, times delta 1 prime, delta 2 prime, delta 3 prime, delta 4 prime. Right? Okay. Which is the same as saying EA over L, okay, basic stiffness, times gamma RBM times delta prime. Okay. Now, I can further expand this and get EA over L times gamma RBM, okay, times what? Gamma ROT times delta. Okay? Where, recall, this is a displacement vector in the global coordinate system. Okay? All right. You see? Now, we can also work backwards, right? Given the basic force, okay, I can write down the expression for F prime as gamma RBM transpose, right, times the basic force vector, right? Okay. But I just developed the expression for the basic force vector, which I can write down here. Gamma RBM transpose. Here I have my basic stiffness, EA over L, times gamma RBM times gamma ROT times delta. Okay, very interesting. Okay, and then finally I can write down the expression for F, right? Force vector in the global coordinate system as gamma ROT transpose, right, times F prime, okay, from the earlier relationship that we developed. Okay, and then I can go ahead and substitute all this into F prime. So as the end result, I get this. Gamma ROT transpose, gamma RBM transpose, basic stiffness, EA over L, gamma RBM, gamma ROT, I'm sorry, times delta. Aha. So what do we have? This is my force vector. Force in global coordinate system. Okay, what is this? This is a displacement in the global coordinate system. In global coordinate system. Okay. And the two vectors are related by this kind of a seemingly cumbersome object. Okay. All right. And so now let's see, let's trace the dimensions. This is 4 by 1. This is 4 by 1. Right? Okay. Gamma ROT, 4 by 4. Right? Gamma RBM, 1 by 4. Right? EA over L, 1 by 1. Gamma RBM transpose, 4 by 1. And gamma ROT is 4 by 4. Okay? And so this gives me a matrix that I'm going to call K, 4 by 4, right? And because this is the matrix that relates displacements to forces, okay, I'm going to call this the truss or bar element stiffness matrix in the global coordinate system. Okay. Let me take a step back. Okay. We also have another object that emerges here. Right? I have f prime, right? And then gamma ROT times delta is going to be delta prime, right? And so we have another relationship, okay, that relates forces in a local coordinate system to the displacements in the local coordinate system. And that object is given right here. I'm going to call this guy kappa prime, okay? And then kappa prime is going to be gamma RBM transpose EA over L gamma RBM. Okay. So this will be truss or bar element stiffness matrix in the local coordinate system. Okay, so of course this object is perhaps not so important, although it is used, right? The key is this guy for implementation. Of course, you want everything in the global, as I mentioned before. This is how you're going to solve your structures, right? But yeah, the structure is important, right? As you can see, right, the object that emerges in the center here is our kappa prime over bar matrix, okay? And then kappa prime over bar is just EA over L, and this is a truss or bar stiffness matrix okay, it's actually a simple 1-by-1 matrix in the basic coordinate system, right? And so you can see the structure. The way you build up the stiffness matrix is you start at the basic level. Okay? You use the RBM matrices to get you to the local level, okay? And then you use the rotation matrices, pre and post multiplication, to get you to the global level. Okay, it's a very interesting structure that emerges. Okay, well, let's see what it looks like. Okay, so let's start with kappa prime. And let's work out explicit expressions for these things, right? Gamma RBM transpose is -1, 0, 1, 0. Okay, this guy goes and multiplies EA over L, okay, and multiplies gamma RBM, -1, 0, 0, 1, okay? And so if you carry out the product, you sort of leave this up to you, okay? You get a 4-by-4 matrix that looks like this. EA over L, 0, minus EA over L, 0, 0, 0, 0, 0, minus EA over L, 0, EA over L, 0, 0, 0, 0, 0. Okay? Good. So this is the same expression that's given on page 213. Okay? And so what you recognize here, by the way, right, is an expanded version of the truss stiffness matrix that we derived in the first lecture. Right? Except that, right, you can see that the structure of the matrix such that the second column, fourth column, second row, fourth row are exactly 0, right? These are the rows and columns that couple the vertical components of the displacement, right? There are no vertical components in in a local coordinate system, right, the only components that remain are the horizontal components, right? And so in the horizontal components, you precisely get the structure of EA over L minus EA over L minus EA over L, EA over L, right? So this is precisely truss stiffness matrix with rows or columns corresponding to vertical displacement removed. Okay, it's interesting, right? That one we arrived to by solving the differential equation, right? This one we arrived to by starting in the basic system, which again also falls out of the differential equation, and applying sort of a formal matrix-based procedure. Okay? Okay, now that we have the local guy, okay, we can compute the global guy. Okay? For the computation of the global guy, we're going to define the following quantities. Cosine phi, we're going to denote by C. Sine phi, we're going to denote by S. Okay? And so in that case, right, you need to multiply the following. C minus S 0, 0, S C 0, 0, 0, 0, C minus S 0, 0, SC. Okay, this guy will go and multiply EA over L 0 minus EA over L 0, 0, 0, 0, 0 minus EA over L 0, EA over L 0, 0, 0, 0, 0, right? So let me continue on the next line, right? And this will multiply a rotation matrix. It looks like this: CS 0, 0 minus SC 0, 0, 0, 0 CS 0, 0 minus SC. Okay, so this was our gamma ROT, if you recall, right? And this is our gamma ROT transpose. And so if you carry out the multiplication, you get the following result. You can factor out EA over L. You get a 4x4 matrix here. Okay? And here you have the cosine squared, sine cosine, minus cosine squared, minus sine cosine, sine cosine, sine squared, minus sine cosine, minus sine squared, minus cosine squared, sine cosine, cosine squared, sine cosine, minus sine cosine, minus sine squared, sine cosine, sine squared. Okay, so that's the structure that you get, and again, I send you to equation 221 on page 213 of the notes. Okay, all right. And so this is what I wanted to cover this week. Okay, we derived important object, okay, the stiffness matrix for the truss element, okay, and you can see how the material parameters, namely Young's modulus, right, or elastic modulus, area parameter, right, length, and spatial orientations, right, all come together to form this important object. Okay. I'm going to stop here and continue later.